Okay, so today I'm going to introduce you to a classical problem in Olympiad mathematics. So the problem is about the bugs on a board, and the problem can be stated as follows. So we have bugs that sit on a 5x5 board, so that we have one bug in each cell. So then all these 25 bugs simultaneously move to adjacent cells. Can it be that after that again there is exactly one bug in each cell? So this is the problem. So now I'm going to explain this setting. So we have a board 5x5 and there is a bug sitting in each cell, as you can see on the picture. So then each bug moves, and it can move only to one of the 4 adjacent cells. So for each bug there are only 4 options to move. Of course, for the bugs that are on the edge of the board or in the corners of the board, there are less options. So then the question is, can it be that after these moves, after all of these 25 bugs move to adjacent cells, can it be that after that again we have basically the same distribution of bugs? So each cell again contains exactly one bug, so that there are no empty cells and there are no cells with more than one bug in it. So basically this is the problem, and this is a very classical problem in Olympiad mathematics. I don't know the origin of this problem, but it is very well known. So then I will present you the solution. So if you want to if you don't know this problem and if you want to try to solve it on your own, then this is the place where you should stop the video and return to it later if you want to know the solution. Okay, so now let's go into the solution of this problem. So the main step in the solution is to color the board. So we color the board in 2 colors, black and white, exactly as is shown on the picture, and this is basically the standard chessboard coloring. So what are we going to do now? So let's make 2 observations. So the first observation is that in this coloring the adjacent cells always have different colors. So if you take any 2 adjacent cells, one of them is always white and the other one is always black. There are no 2 cells that are next to each other that have the same color. Okay, so it follows from this that when a bug moves to an adjacent cell, it always changes the color of the cell. Okay, so all these 25 bugs, when they move, they change the color. Okay, so the second observation is that in this coloring we have 25 cells, and the number of black cells is not the same as the number of white cells. So we have 13 black cells and 12 white cells. Okay. So now from these 2 observations we can conclude that it is impossible that after the move, exactly one bug would be in each cell. Well, because why is that? Because each bug changes the color, but we have 13 black and 12 white cells. So basically it means that initially we had 13 bugs in black cells and 12 bugs in white cells. So after the move, 13 bugs that were in black cells, now they will be in white cells. So we have 13 bugs in white cells, but we have only 12 white cells. So if you play, it's impossible to place 13 bugs in 12 cells, so that there will be exactly one bug in each cell. So there will be at least one white cell where there will be more than one bug, and there will be at least one black cell that is empty after the move. Okay, so this is basically the solution, that's it. So what I want to stress here is that the non-trivial part, the only non-trivial part in this solution is, of course, the coloring. There was no mention of the coloring in the setting of the problem. There was no coloring there. It was just a board, that's it. So we introduced this coloring, and this is really non-trivial. Okay, so now I want to make a remark about some connection to graph theory. So suppose for a minute that what does it mean that after the move all the bugs are again one bug in each cell? So it means that all these bugs can be separated into cycles. So one bug moves to another cell, the bug in this cell moves somewhere else, in this cell the bug moves somewhere else, and so on, and sooner or later we need to if we go one bug by one bug, then this should be a closed cycle. There is no other possibility, and so then if there are remaining cells, then we repeat the same procedure again. So it means that if this move were indeed possible, then all the bugs would be separated into disjoint cycles. Okay, but the number of so, and this by the way we imagine as a graph. So the number of vertices in this graph, which is like the cells, is 25, and this is odd. So it means that if we separate odd number of vertices into disjoint cycles, like at least one cycle should have odd length, because if they all have even length, then the sum of even numbers would be even. So then we would have even number of vertices. So 25 is odd, therefore at least one of the cycle has odd length. Okay, but it is a well-known fact in graph theory that a bipartite graph does not have cycles of odd length. And this graph is bipartite is precisely because of the coloring that we considered. So that like a graph is called bipartite if it can be colored in two colors such that the adjacent vertices have different colors. So this very coloring that we considered in our solution demonstrates that this graph is bipartite. So I just wanted to mention this this connection with some some notions from graph theory. Okay, so basically that's it for this problem. Goodbye for today.